Thank you, Anna, for such a nice introduction. And first of all, I'm very happy to be here. It's my first in-person conference in 3 years since NMT 2019. So I'm very excited, a bit scared of all of you, but I hope it will be okay. And yeah, and first of all, I want to apologize that I'm not going to talk about huge language models. I am going to talk about machine translation. And here I have a story for you, the story of the kind I like most. Where we are going to look at the same process from two different perspectives, and we're going to see that these views show the same results and how they reflect the same process. And this is based on our work with Ivan Titov and Vika Semich. Okay, so when looking at an NMT training process, the two viewpoints will have, and the questions we'll ask and is what is happening on the inside of the model, and then what is happening on the outside of the model. And on the inside, we're going to look at the trade-off between source and target contributions to predictions. And I'm going to explain what that means. And on the outside, we're going to look at competencies the model learns and the order in which that happens. And the part I like most is that in the end, we're going to see that these two views show the same process. But before we start, since any kind of analysis is not done in vacuum and it's done for some task, right? I'm going to give you a bit of context for the task we'll be working with for machine translation at very, very high level. As you know, machine translation came all the way from traditional statistical approaches to end-to-end neural ones. And this transition was rather interesting because it changed the way we think about the machine translation task, its components, and what it means to translate. In traditional statistical approaches, humans, people, researchers decide what it means to translate. They decide which competencies model needs to have to be able to translate. And typically they split translation task into different components. Usually the core components are target side language model and the translation model. And a translation model is in turn split into lexical translation probabilities and word alignment probabilities. And usually there are also lots of handcrafted features. All of them, the important part for this talk is that all of them were trained separately, obtained separately, and then combined together in a single model. In NMT, everything is different. Here we train a single neural network that just reads lots of parallel data and somehow gets to learn the translation task directly without splitting it into subtasks. And at an even more high level, in traditional approaches, humans used to tell model, hey model, take this, that, and this other stuff, and this is how you learn to translate. In NMT, and the model would say, okay, because what else can it do? In neural approaches, everything is very different. Here, model tells us, hey, look how good I am. Reading lots of stuff made me understand things. And here we are, confused, surprised, and asking how. And the question of how is the main question of this talk. And again, the two perspectives we'll have is on the inside and on the outside. And let's start from the first one. Here, we are going to look at the trade-off between source and target information in the model. As you know, in NMT, every prediction is based on two very different types of context: prefix of the target sentence or previously generated tokens and the source sentence. But what is not clear is how the model balances these two types of information, what influences the predictions, the source or the target. And why is this important? Well, broadly speaking, there's a lot of evidence that sometimes models fail to effectively use these two types of information. For example, it can be seen by modular modifications showing that context gates, which way these types of information help for both RNNs and transformer. But a more interesting example is hallucinations. So when a model produces text that is unrelated to the source sentence. And there was some evidence that based on heuristics that sometimes when model is hallucinating, it has deficient attention pattern, deficient attention when all the tokens look either to the source end of sentence token or an informative token such as punctuation. But as we'll show in the other work, this cannot be used as a criteria to identify hallucinations. So, and if you had a method that can estimate the influence of source or target, relative influence. It could be used to evaluate techniques which force a model to rely on input, and I will show you some of it today. And it could also be used to evaluate models for other tasks where reliance on source is more important. For example, data to text generation, image captioning, etc. Okay, now I hope you're motivated enough. I am, but I'm a bit biased here. What do we want? We want to understand what influences the prediction, the source or the target. We don't want just any methods saying what influences more, right? We want to estimate relative contribution rather than some abstract quantity. And for this, we adapt. So what is going to happen, I'll briefly introduce the method, and to illustrate things the method can do, we'll look at a couple of experiments. We'll look at random prefixes, and we'll talk a bit about hallucinations, and then we'll come to the training process. So for the method, we adopt one of the attribution methods originally developed for computer vision. And here the idea is that while the prediction is formed from input to output in the forward parse, this method propagates prediction recursively from output to input to identify parts of image important for prediction. And for NMT, so we adapt this method for transformer with a bit of math. If you're interested in that, you can look at the paper. But high-level notation is the same. So we take a prediction, we propagate the prediction recursively from output to input through all the layers, and we end up with contribution of all the input tokens. And because of the specific method we use, LRP, the total contribution of all tokens stays the same as the prediction we propagate, because it relies on this conservation principle. So when we propagate information, the total influence of everything is the same as the prediction. And that's why we can evaluate relative contribution of tokens or the whole source or target sentence to the predictions. What do we expect here? Well, when we are generating the first token, clearly the prediction is based on the source, right? Because there's no prefix yet. But as we move on, we expect to see that contributions change. So different tokens might be generating different tokens might be based more on the source or on the target. Here used to be a GIF. So imagine that tokens are moving to the right and back, and the predictions, the influences change. And it's very, very beautiful and informative. So basically what is going on here? What we're going to do is for each target position, to evaluate contributions of tokens, and we'll look at the total contribution of the source sentence, because this will show us to what extent the model relies on the source, and at the entropy of contributions. But because in this talk, I'm just illustrating the method, we'll look at the total source contribution, and I'll show you a couple of examples. Since we want to understand, for now, we want to understand model behavior in general, we do this on average over a data set. So we have a development set, and for each target token in each sentence, we evaluate contributions, and then we average. So we have source contribution at each generation step, and then we take an average. And then we say, okay, generally, on average, the pattern is as follows. The model behaves like this, right? And specifically for this figure, first of all, let's look at a single model and see what it's doing. So this is, as it's common in the machine translation, model trained on news translation task, WMT data. And on the x-axis is the target token position. On the y-axis is the source contribution. And generation progresses from left to right. So from left to right, we can see how the contribution of the source changes. And we start from position 2 because for position 1, contribution is always 1, the source contribution. Okay, so what do we see? We see that during generation, influence of the source decreases, and it's kind of expected because the further along you're during generation, on the one hand, the less ambiguity you have in which source tokens to rely on, right? Because you already generated something. And on the other hand, when translating neural machine translation system, because it's doing everything at the same time, it has to stay both adequate, rely on the source, and fluent. And the longer prefix you have, the more effort is needed to account for the prefix, right, to be fluent. So this contribution decreasing from translation perspective makes sense. What is also interesting is that for the final end of sentence token and punctuation mark, the source is used much less than for all the other tokens, and the target prefix is used more. It means that decision to complete generation is based not on the source, less on the source than on the target. So when the model is deciding, okay, I'm done translating, decision is made based on the prefix. This was one model. Now let's compare different settings. And here again, I'm showing you only a small fraction of the experiments we had just to illustrate the capabilities of the method. And here, so far we looked at prefixes of reference translation. So this is the same setting as during training, right? And now let's look at random prefixes. And the question I'm expecting is that, Lena, why on earth are we looking at random prefixes, right? It doesn't make sense. So the setting here is that we have a source sentence that means something like, I saw a hungry cat on a mat yesterday. And we have a prefix of a random sentence, for example, the man in blue shirt. And we're looking at contributions with what the model is doing when conditioned on these two types of information that make sense separately, but not together. And the reason we are doing it is that one of the motivations behind looking at the contributions is to work on hallucinations in NMT and more generally in NLP. And this is the simplest way to simulate hallucination mode. And so let's look at what's going on. Before we look at the results, let's think about what we can expect. On the one hand, so we have two different types of information that don't make sense together, right? So which part the model will support, the source or the prefix? And from previous work, on the one hand, we know that NMT models can hallucinate. Something is going on. Is it? Okay. Okay. From previous, oh my. Okay, from previous work, we know that NMT models can hallucinate, right? It means that the decoder can ignore the source and generate from its language mode, right? On the other hand, there was work on language modeling that showed that language models can ignore gibberish prefixes and continue generating sensible text. So they have this self-recovery ability when they can just ignore the prefix and do something reasonable. So in our case, where we have the source and the prefix, which part will our model support? So what will it do? And what we see, so the red line now is the same graph. I just added one line for random prefixes. And what we see is that even when given one random token as the prefix, the source contribution drops quickly. It means that the model, when something is wrong in the prefix, it quickly starts to hallucinate. So it drops the source contribution and start hallucinating. So there's no self-recovery ability. The NMT models are very fragile to errors in the prefix. And since we're talking about errors in the prefix, let's talk also a bit about how this is related to exposure bias, right? Because when we're generating translation, this might be one of the problems. So there's a chance that the tendency of a model to hallucinate is related to the way it's trained to exposure bias, right? Because previous work compared two models, one trained with a standard objective, maximum likelihood, and another trained with minimum risk training that does not suffer from exposure bias. And what they observed is that hallucinations the models trained without exposure bias suffer from hallucinations less. And they hypothesized that exposure bias leads to over-reliance on target history. And this was at ACL 2020. And this was just a hypothesis, right? There was no way to measure this reliance on target history. And now since we have a method to measure reliance on target history, we can measure this directly. So let's do that. We'll consider models, the baseline model, which suffers from exposure bias, a model trained with minimum risk training, that does not suffer from exposure bias, and also two simple modifications to training, which will word dropout on the source side and word dropout on the target side. This is a setting where some tokens are replaced with random tokens. And when applied on the source side, the model still suffers from exposure bias because it sees only reference prefixes, right? And when applied on the target side, we can say that it suffers from exposure bias a bit less because, in a sense, that during training, the model sees other than good reference translations. And what we see here, and again, I'm showing you only the experiment with random prefixes, hallucination mode, but in the paper we also have normal prefixes and what happens when the model generating translations, and the results are basically the same. So here, what we see is that with minimum risk training, source contribution is a lot higher than for the standard model. It means that without exposure bias, even when given random prefix, the model still tries to take information from the source. It tries to recover. Then for target side word dropout, which also suffers from exposure bias, but less than the baseline, we also see an increase in the source contributions, right? So overall, we can say that indeed, less model suffers from exposure bias, less it's prone to hallucinations and over-relying on target. Yeah, so this is the conclusion. So that models suffering from exposure bias are more prone to over-relying on target and hallucinating. But at this point, we are done with the part that is supposed to illustrate the abilities of the method, and now let's apply it to look at the training process. In this part, we take different checkpoints during training and evaluate the total contribution of the source. And what we see here is that changes are not monotonic, right? So we would expect to see some graph where something is going on, contributions are doing something, right? But what we see is that changes are not monotonic. The contributions go down, then up, then almost nothing is going on. It means that the training consists of stages with qualitatively different changes, right? And we can and the same goes on when if we look at entropy. So the stages are the same. Something really interesting is going on during NMT training, we can hypothesize that, for example, when the source contribution decreases, the model ignores the source and maybe hallucinates, right? And then when the source influence goes up, the model learns how to use it. But so far, these are just hypotheses, right? We cannot know for sure until we look at the output, right? So what is really going on? And to answer what's really going on, let us look on the outside. Right, and here again, look on the outside. What does it mean? To know where to look at, we again remember how things were done in SMT. I'm not grown up enough to remember that, but I did my homework because when I started my PhD, there were already neural models and transformer just appeared. So, but I did my part and. At a high level, in traditional approaches, the core components of the model were target size language model, lexical translation probability, word translation probabilities, and reordering probabilities. And these competencies were modeled with desync models, so they were put together in a model, and then were trained separately and then combined together. In NMT, again, everything is happening in a single network. And here the question is, how does NMT acquire these competencies during training? For example, are there stages where it focuses on learning different competencies, or does it learn everything at the same rate? Does it learn word by word translation first and more complicated patterns later, or is there a different behavior? And we are about to find out. And once again, before we looked at models' inner workings, and we saw that the training process is non-monotonic, meaning that there are stages with qualitatively different processes. And now we are going to look at the model outputs during different steps in training. And we're going to focus on the competencies related to 3 core SMT components. So we're going to look at target size language modeling, lexical translation, and geodeling. And for this, we're going to evaluate language modeling scores from KNLM. It's an N-gram model, translation quality, and Monotonicity of Alignments. And here I will also have some examples to show you. So we'll be actually able to see how the model gets done translation. Okay, first, let's look at language modeling scores during training. So for each step during training, we use checkpoint at the step to generate lots of translations, and we evaluate language modeling scores. And first, here we see that most of the change is happening very early in training in the scores, right? And we see that the scores go up and peak much higher than the scores for references. So the scores for references are shown with the horizontal dashed line. It means that the model generates sentences with very frequent n-grams rather than diverse texts, right? Because for diverse text, you're not going to, for reference, you're not going to see very high language modeling scores and n-gram language modeling scores. And if you look at this early part of training more closely and look at n-gram models with different lengths of context from bigram to 5-gram, we'll see that there's a stage where the scores for simpler models, for example, for bigram, are higher than for more complicated ones, 5-gram. It means that the model at this part of training generates frequent words in bigrams, but larger subsequents are not necessarily fluent. And now let's look at the example. At the top is the source sentence, 6 months of construction works, that's brutal. And on the left, translations to German at different checkpoints during this early stage of training. And to the right is their approximate translations to English. So what we see is that first, model generates the most frequent token, then the most frequent bigram, then the most frequent 3-gram, then some frequent words and phrases in the target language, and finally something reasonable starts to appear. And this is the model learning how target language works. And this is very similar to how, for example, children do it, because they hear some words and they try to mimic, and at first it doesn't make sense in context of what's going on, right? They're just blubbering what they hear. And for example, this year I happened to spend several months in Portugal with the research group there. And after a couple of weeks, then I moved to Lisbon. To me, Portuguese sounded like "Não são obrigado." So this is what the model was doing at the early stage. Okay, so next, let's look at translation quality. And here, I'm sure you saw all this curves, like blue score goes up. That's not interesting, right? It's supposed to go up if we are training that model properly. And also, okay, let's look at token level accuracy for different tokens of different frequency ranks. And also, accuracies go up, which is expected. The only interesting thing we can see here is that accuracy for rare tokens improves slower than for the rest, which is again expected because rare phenomena are learned later. But there is indeed an interesting observation here to make. Namely, if we look at the last half of the training, the scores almost don't change, even accuracy for rare tokens. So from everything we measured during training, the model converged long ago, right? But what is going on? Luckily, we have one more thing to look at, and we'll look at monotonicity of alignments. Here we'll look at, so monotonicity of alignments is like if we look at word translations. So word by word translation, if you're translating from your native language to some other just translated words, this is highly monotonic translation, right? And when you become fluent, it usually becomes less monotonic. So here, lower scores mean less monotonic alignments. And what we see here is that, so this is the same part, last half of training I showed you before. And here we can see that, well, we don't see changes in blue score or accuracies. Alignments are still changing. So the alignments become less monotonic. So the model learns how to reorder, how to translate with more complicated reorderings. And, and even after the model converged, even after that, we see that the alignment changes in the alignments are still visible. And this is one more evidence that using either blue score or concentric pillows as early stopping criteria, or as evaluation metric, or to understand whether the model stopped learning is not suitable. And this is not the first time we are seeing it. For example, earlier in some earlier work, we also observed that for context-aware model, the blue score converged, but discourse phenomena were still improving. And you don't see it with either blue score or concentric pillows. Okay, and here I again have an example for you. So here are two translations, to example, for different models for English German and English Russian, and their translations during this last half of training. And I don't expect you to understand the examples. I wanted to look at the colors. So the aligned chunks are colored the same. And here we can see that at the beginning of this last stage, the translations are almost word by word, right? The chunks are aligned perfectly. And then only later, by the end of training, the alignments become less monotonic. And for example, for the Russian example at the bottom, the green part gets reordered to the beginning of a sentence. And these less monotonic translations are more natural in the target language. For example, this is more natural from the native speaker perspective. Okay, and again, this is also very similar to how humans learn a foreign language, right? At least I did it this way. You usually start translating words, you learn how a word is translated, translate word by word, and then later you understand how things are reordered. Okay, so to sum up what we saw during NMT training, there are indeed 3 stages, and if we had to characterize them, we can say that first, the model learns target side English modeling. Then it learns how to use source and approaches word-by-word translation. And finally, it's the refining stage where changes in typical scores are not visible, but we can see that the alignments are still monotonic. So roughly speaking, it's target side English model, word-by-word translation, then reorderings in this order. And the most interesting part to me, again, if you remember what we saw with their on the inside view, right? We saw that actually we saw the same stages. And so the first stage where source contribution goes down quickly, when we look on the outside, we see that this is when the model ignores the source and hallucinates, right? When source contribution goes up, this is when the model starts using the source and learns word-by-word translation. So after these 2 stages, it's almost word-by-word translation. And at the last part, again, even with contributions, nothing is going on because the model already uses the source. And what it learns is just a refining stage where it tries to use more complicated orderings. And yeah, so this is the end of story where we come to seeing that the process is the same and the 2 different views show the same process. And I'm really happy I get to talk about this at BlackboxNLP workshop because I'm sure you know all the different kinds of analysis. And to me, I'm not very good at trusting results. I used to be a mathematician, and to me, you know, if you proved something, you can be sure. With deep learning, you cannot be sure about anything. So to me, if I have a backup plan, I just feel better. And I really like when different kinds of methods and different methods or different views, like in this case, show the same process. And we can see how this process is reflected in different methods we use. And if it wasn't BlackboxNLP, I would also tell you how this analysis can be applied directly to improve non-progressive NMT system by OneBlue. But if you're interested, you can still look at the papers. And yeah, that's it for both papers. I have blog posts, and that's it. Thank you.